So far, we've considered only situations, or focused on, applications of Newton's second law to situations where the acceleration is a constant. There's an excellent number of problems where constant acceleration is a good approximation. That's fine. I want to reiterate, because I've really been focusing on this, that my Newton's second law strategy is the same in every problem that I do, from the very simplest problem to the most sophisticated. I examine the physical system and understand what motion I'm trying to describe and what the limitations and approximations are to that motion. And then I draw a free body diagram describing all of the forces that influence the motion and their directions. And from that free body diagram, I write Newton's second law very carefully to get the equation of motion. Once I have the equation of motion, I then use that equation and some cleverness and mathematical skill and my reasoning ability to derive conclusions from that equation of motion about the dynamics of the system. That's always my strategy. And that's my strategy here as I solve a problem of particular interest. There's the problem of viscous drag. Viscous drag, which is definitely an essential. I left the S out of viscous. Look at that. I think I'm going to scrub this out. And I left the S out of viscous particularly because while I was thinking about it, students tend to refer to it as vicious drag because they don't necessarily enjoy the mathematics involved encountering it for the first time. But viscous drag refers to what is typically referred to as air resistance. As an object moves through the viscous medium of the air or water or syrup or any kind of fluid medium, that fluid offers some resistance to the motion. Now, there are some details to that we won't consider in our physics. That is, the density of the fluid and the cross-sectional area of the object. That is, there's a way of describing mechanically how much viscous drag I should get in any particular physical system. We're not going to get into the details of where viscous drag comes from. We're going to describe that force in general and derive some consequences of that. So the very first thing that I'm going to do, the simplest version that I have, which is quite essential to be able to do this derivation, is imagine that I have a flat surface here, and on it there's a vehicle that has some wheels, so that I'm not going to consider friction. So I have like a little car here, perhaps. And the car is moving along with a velocity v0, but there's no engine providing a forward force. That is, this car does not accelerate. If I do not consider any viscous drag at all, then what Newton's first law tells me is that this car will proceed to the right forever and ever and never stop because it has inertia, and its natural tendency is not to accelerate. But I know what will actually happen. The car will go along and eventually slow to a stop. And if I examine that situation, I wonder, what is the cause of that? And I realize that the car is moving through a fluid which resists its motion. And so there's a force associated with that. When I draw the free body diagram for the car, drawing all of the forces that act on it, I'll naturally draw the weight mg directed downward, the normal force N directed upward. Two forces that I won't be considering in this analysis because it is the horizontal motion of the car that is of interest.
Is there any specific name for this?
Any specific what, I'm sorry?
Specific name for this essential.
Viscous drag.
Okay, just viscous drag. Okay, so it says the whole 2 days is viscous drag, so it's just the simplest version of it, I guess.
Yeah.
Okay.
Yeah. So these two forces, the normal force and the weight, are not forces that I'm going to consider because I'm interested in the horizontal motion. And since I don't have any friction force, I probably don't have any need to know the normal force. My interest instead is on this viscous drag force, which I'll just call F sub D. It's a perfectly legitimate name for it, that opposes the motion. So I draw it as a force vector directed to the left because the motion of the car is to the right. Now, as I said, there are some specifics to this that you can get into, and you'll read about in your textbook how to calculate how much viscous drag there should be in any given physical situation. But what I'm going to do is I'm going to model this viscous drag as a force, F sub D, which is equal to negative, and I put a negative sign there only to imply that it opposes the motion of the car. There's no other utility to that. B times V, where B is a constant that is determined by all of those natural things that determine how much drag I'm going to get. Cross-sectional area of the car, the density of the fluid, the temperature, and so forth. All of those things that could potentially affect that are generalized in that coefficient of drag in the same way that the friction coefficient mu describes the very complicated molecular interactions of the surfaces. I'm not interested in the details of that. It's simply the strength of that interaction. So that drag coefficient B in product with the velocity. Well, this is what makes the problem interesting. The faster you go, the more viscous drag there is, and you already know that this is true. If I stand still here, I don't feel the air exerting any kind of net force on me. Of course, there's air pressure in every direction, but it doesn't exert a net force. And as I move across the front of the room, I can feel it like a breeze pressing against me as I move. But it's quite small because my velocity is quite low. And I think all of us have had the experience as kids probably of driving along in the car, parents driving, and you stick your hand out the window and you feel the rather extraordinary force of the air rushing by. Because you have a large velocity, the drag force is large. And so there are lots of situations where we concern ourselves in an engineering sense with the aerodynamics. When objects have to move rapidly through a fluid, we design them in such a way to minimize the amount of viscous drag that we get, because at high velocities, the viscous drag can become quite large. So how much force you get depends on how fast you're going. So now I've generally described how this force is going to work. Now I apply Newton's second law to my free body diagram. Newton's second law tells me that the sum of all of the forces that act, and I'm only considering the horizontal here, is equal to the mass times the acceleration. And right away, I'm going to point out that I know that the acceleration is defined as the derivative of the velocity with respect to time. And there's some utility here for me to point that out right away, that it is the derivative of the velocity with respect to time. Now, for the net force on the left-hand side of the equation, it is negative B times V is equal to the mass times the derivative of the velocity with respect to time. And all of a sudden, immediately, I have an equation that's the likes of which I've never seen before. But it is the equation of motion. It's a simple one because I only have one force acting. There is the equation of motion. I've done it. I've applied Newton's law, and I have my equation of motion. But this equation of motion is unlike any that we've seen before in our physics. Notice that it is a relationship between velocity and velocity's own derivative. It's a relationship between velocity and velocity's own derivative. I cannot solve this differential equation for acceleration, which is what dv dt is, because it depends on the velocity, and I don't know the velocity as a function of time. Any equation that relates a function to its successive derivatives is called a differential equation. There are all kinds of differential equations, and in our physics course we will encounter many differential equations. Here's the thing. Being skilled at physics and engineering, part of that is recognizing common differential equations and knowing how to solve them. So this essential is a very, very critical essential, because this physical system is not the only physical system that has an equation of motion that looks like that. We're going to see this behavior again in completely disparate physical phenomena. So knowing how to solve this equation is a skill that we must learn. All differential equations have, well, a strange sentence. Differential equations have a variety of techniques for solving them. Some of them are quite fun. There are solutions to differential equations where the first step is to guess what you think the answer is. That's a fun kind of math that starts with just, I don't know, I'll guess and see how that goes. And that's the first step of the procedure. It's such an interesting mathematical field that some of you will probably take a course in it called differential equation, where there are all kinds of relationships between functions and its derivatives. It's an entire course that you can take. But through the course of our physics, we'll discover a bunch of differential equations that are absolutely essential to be coldly understood and how their solutions work out. This is just one such. So here I am telling you the technique for solving this particular differential equation. The very first step that I do to solving this differential equation is to solve for dt. This differential equation has a property that only a very few differential equations have, and that is it is separable. It is possible to get everything that is time on one side of the equation and everything that is velocity on the other side of the equation, to separate the variables. That is not always possible, and so you get new and fancier techniques to do that. But in this case, I can. So I want to get dt by itself on one side of the equation. So my first step there is I'm going to divide the m over here. And I'm going to negative b divided by m times v is equal to dv dt. So to get the dt by itself, I'm going to multiply both sides by dt, and I'm going to take the negative b over mv and divide it to the other side. What I get when I do that is that dt, the differential of time, is equal to negative m over b, and that inverted because I divided it over the sign, 1 over v dv. Now, I've separated, I might think, according to your own style, that I've written that in a funny way, but what I've done is I keep all the constants together, and then I keep the velocity dependence together, and then I have the differential of velocity. To me, it's just clearer what's going on there. Now, one of the introductions of the course, I was talking about integral calculus, and that it would not be the calculus itself that was the tricky part. It would be making the thing into something you could apply calculus to. And that's exactly what I've done here. Here I have the differential of time dt, a tiny little bit of time. And in that tiny little bit of time, some nonsense happens, causing a tiny little change in dv. This equation is begging to be integrated. That is to add up all the dt's over time as it goes. The very first t is 0. When I'm moving with a velocity v0, and then I let time go, an infinitesimal amount dt, an infinitesimal amount dt, I want to add up all of those dt's. The reason why I have to do it this way is that in that very first instant dt, the drag force reduces the velocity because there's an acceleration, and in that first dt it slows down a little. But now that it's slowed down a little, now the force has changed, which means the acceleration has changed, which in the next dt, the velocity changes by a different amount. So because the velocity changes continuously and therefore the force changes continuously throughout the motion, I can't do it in all one calculation from the start to the finish. I can't do it as delta t because the velocity changes in every instant in time, and so I have to do it in little steps. So I do it in little steps, little steps, little steps, and then I add up the change of all those little steps. And so what I'm performing here is the integral of dt, which I find is you know that I think that integral sign is unacceptable. Right out of the gate, for at least the first integral sign should be pretty. What's going to look like? Pretty integral sign. There we go. Nope. Try again. Can't do it. Well, I should have, when you came in this morning, I should have been practicing integral signs. I can't keep doing that, so I'm going to leave it at that. The integral of dt, which remember means to add up all the little times, is equal to the integral of negative m divided by b, 1 over v dv. Well, what do I get when I add up all the little changes in time dt? Delta t, the whole chain. And it shouldn't bother you, I hope. May I please set the initial time to be equal to 0? Of course, that would be a sensible thing to do. So delta t is just t, the time that passes. So the integral of dt is very clearly just delta t, or t, the final time. Now on this side, I've got something complicated like, what this negative m over b, what am I going to do? Well, negative m over b is a constant. M over b is the same for every instant in time. M over b is the same for every dv that I calculate for. And so the language that I use, and I know for a fact that you've heard me say it before, the language that I use is that the constant comes out of the integral is 1 over v dv. And so you see where I've ended up here. I ended up with an integral that's simple to do, just as promised. The trick of the physics is taking your physics and turning it into a thing that you can integrate. The integral itself, often, almost always, turns out to be a simple one. But here's the thing. I want to be careful about how I do this integration because when I integrate dv, I don't get v. I get delta v. I get the change in. So this integration has limits. It has to have a starting point and an ending point. Well, I know what the starting point is. The starting point is v0. And I know what the ending point is. The ending point is some velocity later on. You say, well, no, Sean, it's 0. It's 0. It's going to stop. Well, it's true that it stops eventually. But I'd like to have a more sophisticated result where I can tell you what the velocity is at every instant in time, not just that ultimately it'll be 0. We already knew that. So the way I'm going to put notation on this, which I know for a fact, the reason why I'm describing it here is that I have not yet done it in our course, is that at the bottom here I'll write v0 and at the top I'll write v. What that notation means, sometimes referred to in calculus as a definite integral, which is a very sensible name because it's an integral between two definite points, the initial velocity and the final velocity. What that does is just a little bit of notation telling me what the limits of the integral are going to be. Because once I'm done, you're going to see, I'm going to evaluate the initial and final conditions. So the next thing that I do here is I look at this integral and I think, how do I solve that integral? I can't remember. Well, I have a list of integrals on my equation sheet and I look down. It's quite simple because I know that the integral of 1 over x dx is, that's right, the natural log of x. The integral of 1 over x is the natural log of x, and I've either memorized that or I see that on the equation sheet. And by the way, if I have to look at the equation sheet to find it, that's not going to last long, because this is going to happen so often that you'll be like, well, I know what that is. Because it's very, very common in physics for this to happen. So the integral of 1 over v dv is going to be the natural log of v. So the way I'm going to write this, and this is another one of these cases where I would definitely upset the mathematicians. The calculus folks don't like it when I do this, and I don't particularly care. 1 over v, right? That's not right. Why did I write 1 over v? It's the natural log of v. Pardon me, I was thinking about arguments that I've had with math people in the past. Is the natural log of v, but I'm not done, because there are limits to this integration. So a notation that I use is I put a bar there, and I write v0 to v. Because I'm not done with my integration yet. My integration requires another step here. I have to do the final minus initial. Because when I integrate dv, I'm not getting v, I'm getting the change in v. So with this notation here, what it tells me to do is to just do final minus initial. V is the final velocity, v0 is the initial velocity, so this is negative m over b, multiplied by the natural log evaluated at v, and this is part that the math folks don't like. It really chokes the math people that the variable here has the same name as one of the limits. You'll never see that happen in a calculus class because, I mean, they're technically not the same thing. This is the variable v, and this is its final value. I don't particularly care. It doesn't bother me. Minus the natural log of v0. There. That's my result. And that whole thing is equal to t. Now, every once in a while, we have these little knickknacks of mathematical knowledge that we need. There's a rule for the difference of natural logs. The difference of natural logs is equal to what? Does anybody remember that rule?
It's the division.
Like the ln of v.
That's right. The difference of natural logs is equal to the ratio, so the time is equal to negative m over b, I still have that constant out in front, the natural log of v divided by v0. So now what I have from, notice that after I've completed this process of calculus, my final result no longer has any differentials in it. It no longer has any differentials. It has explicitly the time, a certain number of seconds. It has the mass and the drag, that's fine. It has the velocity at any time t. Name a t over here, that's a specific velocity. And it has the initial velocity, which is a constant of this system. It's the velocity that I started with. It's a number that doesn't change. So we look at that and say, so now I know time as a function of velocity. Well, that's weird. That's not what I wanted. What I wanted was velocity as a function of time. What I wanted was velocity as a function of time. It's okay. All I have to do is invert this equation. To invert the equation, though, is a little bit peculiar. My first step is going to be to take my m over b and throw it over here with the time again. I'd taken it over the other side just for the sake of separating the variables, but now I'll bring it back. By the way, style-wise, I could have left it. But that, is just not the way I do things, I guess. That's the only thing to say about that. So negative b over m times t is equal to the natural log of v over v0. And I know we all know how natural logs work, well, how all log functions work. The natural log is e raised to a power. That's what the log is all about. So what it's telling me is, what the natural log gives me is, what power do I need to raise e so that the result would be v over v0. So what I'm going to do in order to solve this is exponentiate both sides of the equation. For a while, I thought that I had made up that name, like physics fundamentalized. Fundamentalized is not actually a word. And the joke of that title for this whole lecture series is that sometimes I just make words up. There's another word that I made up, that's sophisticify, which is not a word. But it's just to take a thing that's rather simple and add some stuff to it to make it more complicated, which is something that happens all the time in our physics. But exponentiate is a thing that I just made up. But then it turns out we looked it up and found out that's exactly what the process is called. To take both sides and raise the exponential, like the Euler number, to that power. So you can't, the words, it's difficult to describe. I'll exponentiate both sides of the equation. What that means is e to the minus b over m times t. That is, I take the exponential and raise it to that power that would result in v over v0. And so there's that. And so now I've come to my final answer by multiplying v0 over to the other side of the equation. So v is equal to v0 e to the minus b over mt. That is the velocity as a function of time. And that is a good reason why you don't see that in an introductory physics class, because obviously the mathematical technique was sophisticated. I want to stress upon you again, I know I'm really beating a dead horse with this one. I look at the physical system, I draw a free body diagram, I apply Newton's second law. It gives me an equation of motion, which I solve using my mathematical skill and reason. It's challenging. Fine. And then I get my velocity as a function of time. Very often my Newton's second law analysis gives me the acceleration. Well, here it gave me the velocity as a function of time. That's just the result of going through this analysis. Let me think about what this equation tells me. I had asked you, as a favor, in the introduction to the course, to be very familiar with exponential functions and how they behave. This is a decreasing exponential function. Notice the negative sign in the exponent. E to the minus. And so e to the minus is exponential decay. It is an important skill for you to have to be able to draw a graph of what you expect this to look like. And as a matter of fact, on our exams, you'll often be asked to draw the graph that shows what the behavior looks like. Well, naturally, if I make a graph of velocity as a function of time, that velocity is going to start here at v0, the initial velocity. That's where the graph starts. But now it exponentially decays to 0. And so I'll start here and I'll draw something sort of an exponential shape as it goes asymptotically approaching 0. Does that make sense? Sure. Because as time goes along, the velocity will get lower and lower and lower and lower and lower, and it'll eventually approach 0. There's a funny little detail here. According to this theoretical approach, it never actually reaches 0. It just asymptotically approaches 0, which means it never ever stops. Well, that's the limitation of this analysis. That's not reality. Because eventually the velocity gets small enough that the measurement of the velocity has an uncertainty that's larger than the velocity itself, and you've come to rest. You can choose for yourself an arbitrary criterion, at which point you would say, yes, at that time it has come to rest because the velocity is millimeters per second, in which case it has come to rest. Also, a real physical system would have friction force in addition to this viscous drag force. If there were friction force in my free body diagram as well, then that friction force would appear in the differential equation as well. And obviously, making for a more complicated Newton's second law equation, the end result would be more complicated. Yeah, it would be a constant. And so, as the viscous drag really started bringing it to rest, the friction force would ultimately bring it to rest. Because with the constant friction force, now I have a definite time at which it is going to be exactly 0. And of course, that's the way the real physical system works. So this little quirk of asymptotic approach is an artifact of the simplicity of the system.
So will we need to draw a graph for the essential we make for you?
Yes, yes. This is what I would call essential. This is my expectation that you would be able to write this down. But I'm going to go a bit further with it. I'm not going to stop here. But if I were to ask you to sit down and write this one for me, I would say that this is far enough. Yes. So what I've managed to get here is the the velocity as a function of time, which I'll rewrite. That the velocity as a function of time in this problem is equal to the initial velocity, e to the minus b over m times t. That's the velocity as a function of time, which is a good get from my Newton's second law equation. It's accomplished a great deal. It's remarkable. But I would also like to know what is the acceleration as a function of time and what is the position as a function of time. So what I'll do is appreciate the fact that the acceleration is equal to the derivative of the velocity with respect to time. This, by definition, indicates to me that I can obtain the acceleration simply by taking the derivative of this velocity function with respect to time, which is going to be very easy to do from a calculus point of view, but some of us are still getting our calculus sea legs, so I'll go a little bit carefully with this. This is V0 I meant to write out in front, the derivative with respect to time of V0 e to the minus b over m times t, where I'm thinking about my differential here or my derivative here as an operator that chews on that thing and gives me the result. I'm going to do it two ways. I'm going to first do it the cowboy calculus way, right? Just using my instinct, the way I actually do calculus, and then I'll give you a redo of a thing that I've already done, as I'll do it in a very calculus-y sort of way, so you see all the steps go. But what I know about my exponential function is it's the indestructible function. And so when I take the derivative of this with respect to time, the exponential will survive. And so my answer will have e to the minus b over m times t in the answer, because the exponential function is the indestructible function. But what I have to do is take the derivative of the exponent, which is negative b over m, and multiply the front by that exponent. So I take the derivative of the exponent comes down. So this becomes negative v naught b over m. The t doesn't come down because the t is the variable, so the t stays in the exponent. So that's how I get the result in a cowboy calculus sort of way. I just have take my exponential, repeat it, and then take the derivative and multiply. That's how I do that in a cowboy calculus sort of way. How do I do it in the actual calculus way? Well, what I do is I make a u substitution. And I say, let u be equal to the value of this exponent. So u is equal to negative b over m times t. And then I take the derivative of u with respect to t. So du dt is equal to negative b over m. So now what I'm left with is taking the derivative, leaving the constant velocity out in front, the derivative with respect to u of e to the u, which of course is e to the u. But the derivative with respect to u is not what I wanted. The derivative that I wanted was the derivative with respect to t. But if I take the derivative with respect to u multiplied by the derivative of u with respect to t, then I get that cancellation in the what do you call it, the chain rule. And so by multiplying these two results, I get my answer. And so my result is negative b over m e to the u, which is u was chosen to be negative b over m times t. So negative b over m times t. And I had, in this analysis, had left the constant velocity out of the derivative just because I didn't want it hanging on. So there it would appear in the numerator, and so I get the same result. So after I do enough of these exponential derivatives, I realize what's happening is the exponential will always survive the derivatives. It is indestructible. And I simply multiply by the derivative of the exponent, and then I have my result. So that gets me the acceleration as a function of time. Does that make sense? You might look at it and say, well, strangely, it's the same equation, essentially. It has the same time dependence. If I draw the acceleration as a function of time, the acceleration starts out at some maximum value. The maximum value of the acceleration is the coefficient that appears here in front of the acceleration. The maximum acceleration is negative v naught b over m. The maximum acceleration is negative v naught b over m, which, if you investigate these units, turns out has units of meters per second squared. It's an acceleration. That's always true of the coefficient of the exponential. The coefficient of the exponential is the maximum value that a thing has. So I'm going to write this as negative v naught b over m. You see a thing that I've done perhaps carelessly. This axis, acceleration axis pointing upward, is actually the negative axis, right? It's actually negative upward on this graph. That's fine with me. I don't have any reason to trouble myself with making the graph upside down and creating any sort of confusion with that. So the acceleration decreases exponentially. That's mathematical. Does it physically make sense? Well, of course it does. When I start, I have the highest velocity I'm going to have. So I have the largest viscous drag force I'm going to have. With the largest force, I have the largest acceleration. And then that acceleration is going to decrease as a function of time, because as that force acts, I go slower. As I go slower, the force is less, the acceleration is less, and it's less and less and less and less and less. So just like the velocity, the acceleration decreases exponentially to zero. Now I would like to find the position as a function of time, which is going to be a little bit trickier to get, just a little bit. But it's going to be certainly a mathematical exercise, not a physics one. Just the analysis will be physics. Recall that the velocity, which I know, the velocity v, which I know is a function of time because the velocity is v naught e to the minus b over mt, that the velocity is the derivative of the position with respect to time, dx dt. So there's x, but I've got to get it. In order to get it, I'm going to rearrange this equation, dx dt, and solve it for dx, and get a little differential of x is equal to v times infinitesimal time dt. I've simply multiplied dt to the other side of the equation. That is dx. If I add up all of the little dx's, I get the whole change in x, delta x. So what I'm going to do here is appreciate the fact that the integral of dx is equal to delta x is equal to the integral of the velocity with respect to time. But I know what that velocity is, so the integral that I'm performing is the integral of, I forgot what it was off the top of my head, v naught e to the minus b over m times t dt. That's the integral that I have to perform. But be careful. There are limits on this integration. You might look at it and say, well, indestructible function, the exponential will appear, and then you just have to invert the thing or whatever, and I'm going to do that. But there are limits on the integration, and that's going to really change the functional form of the outcome. What are the limits? I start at t is equal to 0, and I go to time t. I start at t is equal to 0, and I go to time t. So, starting here, t is equal to 0 to time t, I'm going to integrate this. Well, the integral of the exponential function is easy to perform. I'm going to have a negative mv naught over b e to the minus b over m times t. That's fine. In order to check to make sure I'm correct about that, take the derivative of this. When I take the derivative, the exponential survives, and the negative b over m comes down, and when the negative b over m comes down, it cancels the m over b. And I get exactly that back again. So antiderivative, thinking antiderivative, that's the way that it works out. Except, careful, 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 I'm evaluating this from 0 to t. So I'm not done yet, because delta x, the displacement, which is what I get, delta x, the displacement, is going to be that final minus initial. Let me just put the constants in front. mv0 divided by b, e to the minus b over mt, but I'm evaluating that now. The final is e to the minus b over mt evaluated at t, which is just e to the minus b over m times t, minus the function evaluated at 0, e to the 0. Because when I put 0 in for t, it becomes e to the 0. E to the 0 is 1. E to the 0 is 1. And so this becomes 1. You know, it's a strange thing when I look at this equation that I've got a negative sign out front, which sort of makes it look like the displacement is negative. That's going in the opposite direction. Something's terribly wrong. Nothing's terribly wrong. Because this quantity inside the brackets, if you observe it, this exponential is always going to be less than 1, which means inside the brackets that's always going to be a negative number. So it is actually positive. So what I do instead is absorb this negative sign into these brackets, which reverses the order of the difference there, and I have m v naught over b times the quantity 1 minus e to the minus b over m times t. Again, at the beginning of the course, I asked you to appreciate the exponential function so you would know what their shape is. And I said that, curious as it was, 1 minus e to the minus x was a function that I'd like to know and to be familiar with. There it is. This behavior, what is it? I can, of course, set the initial position equal to 0. So delta x, I could just call that x, right? I could just call that x. So let me make a graph of x as a function of time with the assumption that the initial position is equal to 0. So at t is equal to 0, my position is 0. Where do I go from there? Well, in order to understand that, let time go to infinity. Let me let time go to infinity. In my function here, 1 minus e to the minus b over mt, when t becomes infinity, e to the minus infinity becomes 0. If I let this exponential function, this decreasing exponential, decrease forever, it becomes 0. So this simply becomes mv naught over b, a constant. Final position, which is the ultimate position that the object or the car, which is what we were working with, will have. So here on this axis, I'm going to write ultimately what the final position is going to be at t is equal to infinity, mv naught over b, and create here a dotted line. Somehow I've got to get from 0 to that line. But I can't just go there. I have to get there in an infinite amount of time, which is why my final result, mv naught over b times the quantity 1 minus e to the minus b over mt, makes a lot of sense, because I know that that function is an exponential that looks like this. An exponential that starts at 0 and then asymptotically approaches a maximum value. This kind of behavior is pervasive in physics. I'll see it all the time. And so this analysis is going to become very familiar. So there we have a new kind of Newton's second law analysis that we do. We drew a free body diagram with a new kind of force in it, and that force depended on the velocity itself, which gave me a differential equation that I had no choice but to use new sort of sophisticated techniques to solve. I integrated it, got the velocity as a function of time, took its derivative to get the acceleration, and integrated it to get the displacement.